Bismillahirrahmanirrahim. Welcome to the Electrical Engineering YouTube channel. In this lecture, I am going to start the section of AC machines. Several equipments which are classified as AC machines are induction machines, synchronous machines, transformers, and alternators. So, first of all, I will start the discussion on induction machines. Then I will move towards synchronous machines. So, in induction machines or synchronous machines, both types this consist of stator and the rotor. The stator of both machine types is the same, and only the rotors are different, and the underlying electrical phenomena which is taking place behind the operation of these machines is also different. In induction machines, electromagnetic induction phenomena actually occurs. So first of all, we will discuss the working principle of stator, and the stator of AC machines consists of polyphase windings, and they are useful for high power applications. They don't require slip rings and carbon brushes, due to which there is no sparking present between the slip rings and the carbon brushes, which is the case with the DC motors or DC generators. So in AC machines, no phenomena of sparking can occur, so they can be used for high power applications. And polyphase supply is required to produce revolving magnetic field in the stator, and the production of revolving magnetic field can be understood by considering these figures. So this is the design, or this is a cross-sectional view of a stator, and this is a two-phase stator, and we can see that first phase AA dash is shown, and the second phase BB dash is shown, whose axis is at right angle to the phase AA dash. So this is a two-phase winding, and in two-phase winding, we know that for a two-phase supply, the phase difference between two phases is 90 degrees, which we can observe from this waveform and from this stator design as well. So the angle between the two phases is same for the supply as for the stator. So here the phase difference is 90 degrees, and same phase difference is available between the two phases. So 90-degree phase difference is present over here, and at several instants of time we can analyze the production of a magnetic field and its orientation. So for example, at the instant t1 we can see phase A, IA is a 0 and IB is a negative. So the convention has been made such that if IB is negative, then this B part will have a dot, or the current is flowing out of the paper, and B dash will have a cross, or the current is flowing into the paper. So if we consider this orientation of the current, the magnetic field direction can be found out by using right hand rule. And when we apply right hand rule, we can see that the thumb will indicate the direction of magnetic field, which is pointing from left to right. So at the instant t is equal to t1, or at this instant, the direction of magnetic field is from left to right. Similarly, at the instant t is equal to t2, IB is 0 and IA is positive. When IA is positive, it means A has cross and A dash has dot. So by this marking of the current, the direction of magnetic field as given by the right hand rule will be from top to bottom. Similarly, when T is equal to T3, IA will be equal to 0 and IB will be equal to positive. So in that case, the direction of magnetic field is from right to left, and similarly at T is equal to T4, IB is equal to 0 and IA is negative. So the direction of magnetic field will be from bottom to top. So we can see that at every instant the magnetic field is revolving, and again at t is equal to t5, we see the same orientation as is given at t is equal to t1. Now we have to derive an expression for the speed of revolving magnetic field, and that speed is also called synchronous speed, and it is represented by ns. And so by analyzing these figures, we can see when one cycle of this AC supply is completed, magnetic field also completes its one cycle. So it means the frequency of the AC supply is equal to the synchronous speed, or Ns is equal to F. So this is a two-pole stator, and we have to multiply and divide this frequency with 2. So later you will see why I have multiplied and divided this frequency by a factor of 2. Now we will move our discussion to a four-pole stator, and for a four-pole stator we will have 8 windings, and this will be AA. These two slots will be designated as AA dash, and these two slots will be designated as A. Similarly, these two slots are designated as B, and these two slots are designated as B dash. Again, we will do the same analysis at several instants, and for a four-pole stator, at t is equal to t1, IA is equal to 0, and IB is equal to negative. It means B will have dot and B dash will have a cross. So according to this polarity of the current, the direction of magnetic field can be marked as shown in this figure. So now we can see these magnetic field lines are originating from this point, and we can assume that they are terminating at this point. So these will can be represented by a curved magnetic field lines. So they will be originated from here and they will be terminated upward. So again, this magnetic field is originating from here and it will be terminated here. So this one magnetic field, uh, this one direction of magnetic field can be considered as having two poles. So this will be the north pole from which the magnetic field lines are originating, and this will be considered as the south pole at which the magnetic field lines are terminating. Similar is the case can be interpreted for these two sets of magnetic field lines, and this will become the north pole and this will become the south pole. So this north, south and north, south. So in total there are four poles in this stator. So at the instant t is equal to t1, we have marked the direction of magnetic field, and at the instant t is equal to t2, the direction of magnetic field is marked over here. Now, from these two figures, we can see that 90 degree of the supply or 90 degree of the phase current has been traveled by the current from the instant t is equal to t1 to the instant t is equal to t2. So this phase separation is 90 degrees. Whereas on the other hand, the revolving magnetic field has been displaced by an angle of 45 degrees in this case, not the 90 degrees. So it means in this case ns is equal to f by 2, and again we have to multiply this expression at the right side with 2. We have to multiply and divide it with 2, so it will become 2f over 4. Now if we compare this expression which is 2f by 4, and here we had 2f by 2, and if we remember, here in this case we had number of poles equal to 2, and in this case we have number of poles equal to 4. It means this constant which is given at the denominator is equal to the number of poles. So we have obtained a general expression of synchronous speed in terms of the frequency and the number of poles. So it will be 2f over p revolutions per second. So this is a general expression for the synchronous speed, and in rpm we have to multiply this expression with 60, so it will become 120 f over p. And this expression is valid for three-phase supply and three-phase winding as well. So this is the expression for the synchronous speed, and suppose if we have a single phase supply, then how would the magnetic field behave? So this is the single phase supply and we have single phase winding, and this is A, and this slot is marked as A dash. At the instant t is equal to t1 and at the instant t is equal to t3, the current is 0 and the magnetic field will be equal to 0. But at the instant t is equal to t2, the current is positive, so this will be the direction of magnetic field, and at the instant t is equal to t4, the current is negative, so the direction of magnetic field will be from bottom to the top. So in this case, we can see that the magnetic field is actually neither rotating clockwise or anti-clockwise. Instead, this magnetic field is pulsating. So it will be from top to bottom, then its magnitude will be reduced, and at the end, its direction will be from bottom to top, and it will be pulsating from top to bottom and vice versa. So in order to produce revolving magnetic field, either we must have a two-phase supply or a three-phase supply, but a single-phase supply cannot be used. And the direction of revolving magnetic field is always from leading to the lagging direction of supply phases. In order to reverse the direction of revolving magnetic field, phase sequence should be reversed of any two phases in a three-phase system. So if we remember, in this case, the phase A is leading and phase B is lagging phase A by 90 degrees. And if we observe the slots, this is A and this is B. So from A to B, we are moving from leading to the lagging current, and the direction of magnetic field is also from A to B, or the direction of magnetic field is clockwise. So clockwise means from A to B, and from A to B, this magnetic field is actually moving, and this is also the phase sequence. Now, if we reverse any two phases, then the direction of revolving magnetic field will be reversed. And here you can see this is phase A, this is phase B, and this is phase C. So this is a three-phase system, and the angular separation between the three phases is 120 degrees, and the direction of magnetic field again in this case would be from phase A to B to C. Now, if we reverse the phases B to C, if we interchange the phases B and C, then the phase sequence will become ACB. So earlier, the direction of revolving magnetic field was anti-clockwise from A to B to C. Now the direction of revolving magnetic field will be from A to C to B, so it will become clockwise. Similarly, if we interchange A and C, again the direction of magnetic field will be reversed. So if we interchange any two phases, the direction of revolving magnetic field will be reversed. Secondly, if we want to reverse the revolving magnetic field, we can either change the phase sequence, or we can either change the sense of binding. So for example, we have the same phase sequence A, B, and C of the supply, but if we change the sense of binding, so this is A, this is B, and this is C, the direction of magnetic field is clockwise. If the sense of binding is this A, C, and B, now it will become this is A, this is B, and this is C. Now it will become counterclockwise. So both these methods can be adopted to reverse the direction of magnetic field. Now, what are the conditions for revolving magnetic field? First condition is the polyphase supply. Second condition is the angular separation or displacement between the windings. So, if there is no angular separation between the slots or between the winding axes, the there will be no revolving magnetic field. So again, in this case, we will get a pulsating magnetic field as was observed for the single phase case. So this is a three-phase transformer, and here we have a polyphase supply, but there will be no revolving magnetic field. Again, similarly for this type of stator in which the winding axes are collinear, then again there will be no revolving magnetic field. So that is all for this lecture. I hope you have learned and enjoyed these topics. For watching more similar videos, please stay tuned to this YouTube channel. Until the next lecture, it's goodbye.